we have to find the longest run of ones in a Boolean vector or scalar. Let's keep that in mind. So let's first have some sample data. And here we can see that we have a run of length 3, of length 2, and a run of length 4. So that will be the answer 4. Let's make a non-anonymous lambda. We can always name it later. And take the argument s. In here we refer to the argument as omega. And we can go directly and cut this into pieces. Well, there is a partition function which takes a mask like this on the left and some data on the right, corresponding length, and it keeps runs of that correspond to ones, and it discards any elements that correspond to 0, and then begins a new partition at that point. It doesn't really matter what our data is, so we can use the same Boolean vector for the data and as the mask, and then we just need to count the length of each one. So this is the tally mark applied to each, mapping over those. We could also state this argument only once by using the selfie operator or commute. So this derives a new function that's the same as this one, but takes one argument and uses it as both arguments of the original. Okay, next step then is to take the maximum, and that is 4. There's one tiny issue, that is, if there aren't any runs of ones, then this gives us an empty list of lengths, and a maximum reduction over an empty list should give us the identity element. That's the argument to the maximum function that will not affect the outcome for any other argument. So that has to be the minimum representable value, and what we're seeing here is indeed the smallest possible 64-bit binary float. So how can we fix this? Well, we can make sure there's at least one value at all times. So we just inject a 0 in front of that, and then it works. However, injecting a 0, this seems like a simple thing. It actually can have an impact on performance. So let's first give this a name, and then we are going to import the compare execution facility from the defense workspace. Let's generate some Boolean test data. So we want it to be in the range of 2. We want there to be 10 million elements of those, and we want them to be random. And then we get random 1s and 2s, but we actually want Booleans, so we compare them to a 1. That gives us, so the 1s give 1, and the 2s give a 0. And then let's think about how we can solve this problem a different way. The problem is that this is a potentially very long list of lengths, and when we inject one element at the front, a 0, then even if we were able to do the transformation in place in memory, we would have to move over every element one step to the right. That's a total rewrite of all the data and a potentially expensive operation compared to everything else that we're doing. So if we didn't do that, then we could end up with this very large negative value. However, any other argument to the maximum reduction would have positive values in it. That is, if we have runs of ones. So what we can do is we take the maximum of the result of this maximum reduction and 0. If it's a very large negative value, we get 0. If it's a positive value, then the 0 is not going to affect it. How big of a difference does this make? Well, let's try it. We apply f on this Boolean and g on the Boolean, and we wait a moment to see which effect this has. That's about twice as fast for 10 million elements. It will vary according to how many elements there are. So this is definitely a good technique. That said, we went, as we can see here in the top left corner, by a nested array that was strictly unnecessary. We could compute the lengths of runs of ones directly rather than actually generating pieces that have these lengths and then measuring the lengths. So how could we do this? Let's start over with our sample data and have a think. If we can find the location of beginnings of a run, and we also find the locations of the ends of the run, then if we subtract the index, the location of every beginning from its corresponding end, that will give us the length. So, how do we do this? Let's go to an anonymous lambda again, and we want to compare adjacent elements. If the left element is less than the right element, and the whole domain is just 0 and 1, then we know that we have a 0 and a 1, and that's the beginning of a run. So we can do a 2-wise less than reduction of the argument. And that gives us the indication where we have this run and this run. Why are we not finding the first one? That's because we never went from 0 to 1. There's no 0 on the left. But we can inject that. Okay? And similarly, if we had been, let's go look at the ends. And this tells us that we have a the end of a run at coming up to this 0 at the end. But of course, let's say there was no 0 at the end. Then we would fail to find the end. So let's put in a additional 0 over here. Okay, so with this, we have our ends, and we also had our beginnings. Now we just need to convert these Boolean masks to be indices. And we do this with the indices function, or where. So this gives us the beginnings, and this, let's change that to the S again, gives us the ends. And if we just subtract the corresponding elements, then we'll get the lengths. Oh, yeah, it has to be the opposite order, of course. We want to subtract the beginnings from the ends. There we go. Of course, this has a lot of duplicated effort. We are generating this 0 followed by the argument followed by a 0 twice. There are a couple of different ways we could solve this, but actually a neat way is to start with somewhere else. We are doing a subtraction, and we're not subtracting these masks, we are subtracting the indices of the ones in the masks. So that's the same thing as subtraction, where we pre-process both arguments using the indices. And we have a higher order function, an operator, for doing exactly that. So this isn't any shorter overall, but it will help us later. So this is a subtraction of the indices. That means we don't need to explicitly compute the indices over here. And now we can see that this lends itself nicely to a fork, because we have a shared left argument and we have a shared right argument. And the only difference here is we have two functions being applied, the less than reduction and the greater than reduction. So this lends itself very nicely to the fork construct. So let's remove everything here and this. Now we have a right argument, a left argument, two functions that are being applied, and the result of those become the arguments to the minus that preprocesses its arguments with finding the indices. And from here on, it should be simple. We do the maximum, but we also want to catch the zero case. So we do the zero maximum like before, otherwise we would have the same problem and performance issue if we inject a zero in the data itself. Let's compare these two approaches then. So we had, oh, did I just overwrite this one? Let's go up and rescue that one. It's this one, and this one should be called H. And now we can compare our fastest of the original algorithm, which was G on B, and this one, H on B. Wait a moment to see. So these are the two approaches of creating runs and measuring the lengths, and computing it directly from the indices. And we can see that makes a huge difference. So that was a nice improvement.